Hello everyone. Welcome to the next lecture on the Mobius transformation. Today I will explain you how you can transform the Mobius transformation into the matrix format. Myself Dr. Harish Garg. You can follow and subscribe my YouTube channel. Now what we have discussed so far, we have learned the concept of the Mobius transformation in our last lectures. You can watch it under my playlist complex analysis. You can see the Mobius transformation pole and the critical point of the Mobius transformations, complex linear transformation, and many more lecture available in this playlist. You can follow and subscribe it so that you can get the notification when I upload the next video. Now, we all know the matrix is used to simplify many of the computational process in the linear fractional transformation. What is the meaning of the linear fractional? It is also called as bilinear transformation, or it is also known as Mobius transformation. How you can think about that? If you have any of the Mobius transformation, then we can convert into the matrix format. How you can write the matrix format? The first, the coefficient, that is a B, and for the denominator part is a C and D. So for any Mobius transformation, we can write the associated matrix A, B, C, and D. For example, if you have the matrix, if you have the bilinear transformation Z minus 1 over Z plus 1, what is the matrix transformation is? The coefficient of the Z is 1, constant term is minus 1, coefficient of the Z is 1, coefficient is my 2. The matrix representation for the first case is 1, minus 1, 1 and 2. Similarly, for the second case, this number is 1, then it is a minus 0.5, minus 3 and 4. And similarly for the last case, how you can write the matrix format? 2, 3, minus 1 and half. So these are the matrix representation of the given transformation. The converse is also true. If you have the matrix formats, if you have the matrix, then you can write the corresponding Mobius transformation. Corresponding to this case is T of Z is AZ plus B divided by C is my 0 plus D. So you can write that the first transformation becomes AZ plus B. Similarly, for the second case, A is my e raised to power iota alpha, B will be 0, C is my 0, and D is my e raised to power minus iota alpha. So you can write the transformation is e raised to power 2 iota alpha into Z. And similarly for the last case, it is my 0Z plus 1 over 1 into Z plus 0. So the corresponding transformation is 1 over Z. Fine. So that means you can write the matrix. You can write any matrix to the Mobius transformation. And if you have a Mobius transformation, you can write in the matrix format. And once we are able to write the matrix format, that concept is very useful. Why? Because once you know the matrix format, then you can easily write the T inverse. You can easily multiply the two matrix and so on. That means we can easily compute the T inverse, T1, T2 and so on. Based on this today's lecture, you can easily, once I will cover the complete this lecture, at the end you are able to answer all such kind of the problem. You can note down these questions, and once you can understand this lecture, you can put your answers in the comment box. Now, the first important property related to the matrix format is if you have the matrix A, B, C, D corresponding to the Mobius transformation AZ plus B divided by CZ plus D, then for any alpha which is my non-zero, if you multiply with the alpha, then they have the same representation. That means this is same as alpha of A plus alpha of B divided by alpha of C and alpha of D. Fine. The proof is a very simple. If you have the Mobius transformation such that AD minus BC is my non-zero, then because alpha is my non-zero, I can multiply both numerator and denominator by alpha. Fine. That number will be alpha plus alpha of D. And if you write the matrix format, corresponding to the this transformation, it's alpha A, alpha B, alpha C, alpha D. And if you take alpha is my common, then the representation is A, B, C, and D. Fine. So therefore, the matrix T of Z is nothing but alpha into T of Z. Hence, the corresponding the matrix representation is the same. Look at the second property. If you have the matrix representation A corresponding to the Mobius transformation Tz, then you can find the T inverse corresponding to the matrix representation A. Now, we all know if you have the matrix, if you have the Mobius transformation Az plus B divided by Cz plus D, then in our last lecture related to the Mobius transformation, we have seen how you can write the T inverse corresponding to this cases. I can reverse the value of the A and D with a negative sign. Fine. B and C are my same. Fine. This is the we have learned in our last lecture. Fine. Now how you can prove with the help of the matrix representation. If you have the matrix representation of A, B, C, D, can you find the A inverse? How you can find the A inverse? That is the adjoint of A divided by determinant of A. So what is the determinant of A? AD minus BC. Can you find the adjoint? It's the minus D, B, C, and minus A. Fine. Now, because we all know AD minus BC is my non-zero corresponding to the Mobius transformation, that implies 1 over AD minus BC is my non-zero. So therefore, by using the property 1, we can, if I consider this number is my alpha, fine, then I can say this representation is similar to the, apart from the real number alpha, these are the same representation. How you can write that? Because this is the inverse, can you write the Mobius transformation? A is my minus of D, B will be B, C is my Cz, and D is my minus A. Therefore, the T inverse is a Mobius transformation corresponding to the matrix A inverse. Another property is if T1 is a matrix, if T1 is a Mobius transformation corresponding to the matrix A, T2 is a Mobius transformation corresponding to the matrix B, then you can write that T2 composition T1, which is same as the matrix representation of B multiply A. You can simply multiply the B into A, you will get the Mobius transformation. Now in this proof is again very simple. You have the two Mobius transformation. I can assume is a A1 Z plus B1 divided by C1 Z plus D1 such that A1 into D1 minus B1 into C1 is non-zero. Similarly, you can define that T2Z corresponding to the A2, B2, C2 and D2. Now, we can define the T2 circle T1. That's a composition mapping. How you can define that? It's a T2 of T1Z. I can substitute the value of the T1Z. Fine. Now I can substitute this the value of the Z. I can substitute the value of the Z into the formula of the T2. That becomes A2 into A1Z plus B1 divided by C1Z plus D1 plus B2 divided by C2 A1Z plus B1 divided by C1Z plus D1 plus D2. Fine. Now you can take the LCM. If you take the LCM, C1Z plus D1 will be cancelled out. It is A2 C1Z plus A2 B1 plus B2 C1Z plus B2 D1 divided by C2 A1Z C2 B1 plus D2 C1Z plus D2 D1. Fine. Now you can make the pair of the coefficient of the Z. This is A1 A2 and B2 C1 of Z plus constant terms A2 B1 plus B2 D1 divided by, again you can take the coefficient of the Z and the constant quantity. Now if you write as a B into A, what is the B? B is my A2, B2, C2, D2 into A, A1, B1, C1, D1. So what will happen if you multiply them? The first quantity will be A2, A1 plus B2, C1. Next quantity will be A2, B1, B2, D1. Then C2, A1, D2 C1, and the last is C2 B1 and D2 C1. Now you can see which is same as of the matrix representation corresponding to the first quantity. You can see this is the same. The constant term A2 B1 plus B2 D1, the coefficient of the Z A1 C2, C1 D2 and C2 B1 D2 D1. Therefore, you can see that T2 circle T1 is a matrix representation of the B into A. Second, next result is the inverse of the Mobius transformation is again the Mobius transformation. That means if you have the Mobius transformation AZ plus B, then how you can find the inverse? Again, it's a very simple, because T of Z is my 1 1 and onto. Once this is my 1 1 and onto, that is a bijective, therefore T1 inverse exists. And how you can define that? If I take W is equal to T of Z, when the inverse exists if and only if T inverse of W is my Z. Fine. T inverse of W is my Z. So I can start from the given expression. W is equal to T of Z. T of Z is AZ plus B over CZ plus D. Fine. Now because this is the result of the if and only if, now you can multiply them. CWZ plus WD minus AZ minus B is equal to 0. Fine. Can you take the coefficient of the Z? CW minus of A, which is equal to minus WD minus plus B. Can you find the value of the Z? Z will be minus WD plus B divided by CW minus of A. And if you compare them, therefore T inverse of W will be minus DW plus B divided by CW minus A is the required answer. Fine. And if you are very surprising to see, if you write the matrix corresponding to the T of Z is A, B, C and D, then what is the A inverse? A inverse will be minus of D, B, C and minus A. Fine. And the one coefficient is AD minus BC. Again, by using the first property, the AD minus BC is a constant. Fine. So they have the same representation. And you can see minus of DW plus B, CW minus A. Now, how you can prove that this is a Mobius transformation? Your target is to prove A. Your target is to prove only AD minus BC is non-zero. A is my minus of D. D will be my minus of A minus B into C. Now that number will be AD minus BC, which is non-zero. Hence, the T inverse is my bilinear transformation. That is a Mobius transformation. Now let's start with the first question. What is given to you? S of Z is Z minus iota divided by iota Z minus 1. So I will tell you the two different methods. The first method is your target is to find the S inverse. So how you can find the S inverse? If the S is my AZ plus B divided by CZ plus D, then how you can write the inverse? I can write a minus DW plus B CW minus A. That means I can reverse A and D with the negative sign. So what is the answer of the S inverse? I can reverse the coefficient of 1 and minus 1. So it is a minus 1, minus of d, that's a plus 1, iota, iota of z, and minus 1. That's the answer of the S inverse. Fine. By using the first method, you can write it directly. So that will be S inverse is 1, if you write in the terms of the W, minus iota, iota W minus 1. Similarly, for the case of the T, it's a T inverse. If you reverse them, it's a minus of 2, minus 1, 1 into W minus of 2. Fine. Or if you write in the terms of the Z, then it can written be as a Z. Second method is you can write the matrix S corresponding to 1 minus iota, iota minus 1. Then you can write the S inverse only taken as the adjoint. So that number will be 1 minus iota, iota minus 1. And again you can see, if you write the matrix, if you write the transformation corresponding to the matrix, you will get the same answer. Now, once we have the Mobius transformation, it always form the group, and the group is known as the Mobius group. And the function is my composition. The pair is denoted by C comma N. Also, if you define the map from the GL2 comma C, that is a matrix, to the transformation is called as a group homomorphism. And once it's a group homomorphism, you can define the kernel, which is defined as K0, 0, K. And once you can define the kernel, we can define the quotient group, that is GL divided by kernel is called as the projective linear group. Okay, now let's say how you can define the S inverse, that's a composition. Fine. I will tell you the two different method again, how you can define the composition. One is with respect to the matrix format. Can you write the matrix format of the S, which is 1 minus iota, iota minus 1? The matrix representation of the T is 2 minus 1, 1 and 2. Because we need the S inverse, so can you write the matrix transformation of the S inverse? I can write the matrix inverse, that is I can reverse the diagonal entries with a negative sign. It's a minus 1, minus iota, iota minus 1. Remember, the only thing is you have to reverse the diagonal entries with a negative sign. If you take the negative of minus 1, it's a plus 1. If you take the negative of the 1, it's a minus 1. Then how you can write that? Basically, this is my matrix representation of S inverse into matrix of the T. So what is the matrix representation is? Equation number 1. What is the matrix representation of the T is? 2 minus 1, 1 and 2. So I can multiply these two matrices. So what will happen? It is my 2 minus iota. Then it's a minus 1 minus 2 iota. Its number is my 2 iota minus 1. And this number will be minus iota minus 2. That is a matrix representation. Therefore, S inverse of TZ. Once we know that it's a matrix, you can write in the terms of the representation A into Z, B minus 1 minus 2 iota divided by C, 2 iota minus 1 into Z, and the D minus iota minus 2 is the right answer of the problem. Second method is, because we know the S, you can write the S inverse. Fine. S inverse, you can reverse them. Fine. Now, S inverse of the TZ. I can substitute the value of the TZ. What is the value of the TZ? 2Z minus 1 over Z plus 2. Now, S inverse. This is the value of the S inverse. I can substitute the value of the Z is, this is the value of the Z. Fine, I can substitute the value of the 2Z minus 1. So this number will be 2Z minus 1 over Z plus 2 minus iota divided by iota into 2z minus 1 over z plus 2 minus 1. Fine. Now you can take the LCM. It will be 2z minus 1 minus iota z minus 2 iota divided by minus z minus 2. Now you can take the pair of the z is common, 2 minus iota, and the constant term is minus iota minus, and from the denominator 2z minus z is z, and minus 1, sorry, it's iota, it's a 2 iota 1 iota, so z will be the common, it's a 2 iota minus 1 and minus 1 iota minus 2, and you can see this is the same as we have obtained from the previous one. Look at the next one. Consider the transformation T, find the T1 inverse, T2 inverse, and so on. Can you write the matrix representation of T1 and T2? What is the matrix representation of the T1? 1, 2, 1, 3. And the T2 will be 1. I can write this number is Z plus 0, 1, and 1. Fine. Now once we know the representation, can you find the matrix representation of the T inverse? I can reverse the diagonal entries with the negative sign, and the rest values are my same. Can you find the T2 inverse? I can reverse the diagonal entries with the negative sign, rest values are my same. So therefore, can you find the value of the T1 inverse of Z? I can, because this is the matrix, I can write in the terms of representation. Minus 3z plus 2 divided by 1z minus 1. Similarly, you can write as a T2 inverse of z. It's a minus 1z plus 0 divided by 1z minus 1 are the answer of the first part, second part. Fine. Now, how you can find that T2 into T1? Now it's a T2 into T1. So again, it's a very simple. You can write the matrix representation of the T2. 1, 1, 1, 0. What is the matrix representation of the T1? 1, 2, 1, 3. So can you multiply them? It will be 1 plus 0, 1. 2 plus 0, 1 plus 1, 2 plus 3, 5. 1, 2, 2, 5. So therefore, similarly, you can write the matrix representation of the T1, 1, 2, 1, 3. T2 will be 1, 0, 1, 1. So if you multiply them, 1 plus 2, that's the 3. 0 plus 2, 2. 1 plus 3, 4. 0 plus 3, 3. What is the matrix representation of the T2 inverse? Minus 1, 0, 1, minus 1. Matrix representation of the T1 is 1, 2, 1, 3. So can you multiply them? Minus 1, 0. Minus 2, 0. 1 minus 1, 0. 2 minus 3 minus 1. Now once you know the representation, now you can write as, for example, how you can write the T2 T1 of Z. The matrix representation is 1, 2, 2, 5. I can write as A plus B CZ plus 5. That is the answer of the matrix representation. Similarly, you can write as a T1, T2, T2 inverse, and so on is the right answer of the problem. Now I hope now you can get the answers of all these 4 questions. Let me know in the comment box if you have any doubt in this lecture. I hope you can like this video. You can share this video with your friends. Very soon we will upload the next lecture on the fixed point of the Mobius transformation. Till then, you can share this video with your friends, like and comment on the videos. Happy learning always. Best wishes.